Welcome back to Mastering Algorithms. In previous episode, we learned about linear search. Linear search is very simple. We start from the first element and check each element one by one until we find what we are looking for. But there is a problem. What happens when we have a very large amount of data? Imagine searching through 1 million numbers. With linear search, in the worst case, we may have to check all 1 million elements. So today, we are going to learn a much more efficient searching algorithm called binary search. Binary search can reduce the search space by half after every comparison. And that is what makes it so powerful. By end of this video, you will understand what binary search is, why the data needs to be sorted, how binary search works step by step, a complete dry run Java implementation, best and worst case complexity, common mistakes, when to use binary search. So let's start with the basic idea. Let's imagine we have an array containing 1 million numbers. We want to find one particular number. If we use linear search, we start from the beginning, we check the first number, then the second, third, and we keep going. In worst case, we may need to check all 1 million elements. Now, binary search takes a completely different approach. Instead of checking one element at a time, it asks, can I eliminate half of the data? And if it can eliminate half, it does. Then from the remaining half, it eliminates half again and again. That's why binary search is so efficient. Before we understand the algorithm, there is one rule you absolutely must remember. Binary search requires sorted data. For example, this array is sorted 10, 20, 30, 40, 50, 60, 70, 80, 90. The numbers are arranged from smallest to largest. Why is this important? Because binary search makes decisions based on the ordering. If we look at the middle and discover that our target, the number that we are trying to find, is greater than the middle value, we know that the target must be somewhere on the right side. Because the data is sorted, we can safely ignore everything on the left. But if the array is random, we can't make that assumption. For example, 40, 10, 80, 20, 60, 30, 90. That is our array. If we look at the middle and see 20 and our target, the value we are trying to find is 60, we can't simply say 60 must be on the right side because the array is not sorted. It might be anywhere. So remember, sorted data is essential for binary search. The entire binary search algorithm can actually be understood using three simple steps. Step 1, check the middle element. Step 2, decide which half can contain the target. Now step 3, ignore the other half and repeat. That's it. We don't search every element. We keep making the problem smaller. Imagine you have 100 elements. After one comparison, you may have only 50 elements left to consider. Then 25, then around 12, then around 6, then 3, then 1. So instead of searching through everything, we repeatedly reduce the problem. This technique is called divide and conquer. Let's understand the algorithm with a complete example. We have a sorted array containing 10, 20, 30 till 90 and our target is 70. Our job is to find where 70 is located. Instead of starting from 10, we are going to start from the middle. Let's see what happens. Our first step is to find the middle element. Here the middle element is 50. Now we compare our target with the middle. Our target is 70. So we ask, is 70 equal to 50? No. Then we ask, is 70 smaller than 50? No. 70 is greater than 50 because our array is sorted. We know something very important. Everything to the left of 50 is smaller than or equal to 50. So none of those values can be 70. That means we don't need to search this entire half. We can completely eliminate 10, 20, 30 and 40. We just eliminated almost half of our search space with one comparison. Now we are left with only 4 possible values 60, 70, 80 and 90. Again we don't start from 60. we calculate the middle of this remaining search space. The middle value is 70. Now compare it with our target. Target is 70 and middle is also 70. They are equal. So we have found our target. The search is finished. We don't need to check 80 or 90. Let's pause and look at the entire process. Initially, we had 9 elements. We checked the middle, which was 50. Because 70 is greater than 50, we discarded the left half. Now we had only 4 possible elements. We checked the middle again. This time we found 70. So, with just 2 comparisons, we found our target. That's the key idea behind binary search. We are not making the computer search harder. We are making the problem smaller. Let's use a slightly bigger example so you can see why binary search scales so well. Suppose we have 16 sorted elements. After the first comparison, we eliminate half. 16 becomes 8. After another comparison, 8 becomes 4. Then 4 becomes 2. Then 2 becomes 1. So we go from 16 possible elements to just one possible element after only a few decisions. Now imagine we don't have 16 elements. Imagine we have 1024. The same principle applies. 1024 becomes 512 after first comparison. 512 becomes 256 after second comparison. And like that, we only need around 10 steps. That's because 2 to the power of 10 is 1024. This is the reason we call the complexity O of log n. Here is a simple real life example. Imagine you are looking for the word tiger in a dictionary. Would you start from page 1 and read every word until you reach tiger? No. You would open the dictionary somewhere around the middle. Suppose you land in the section containing words beginning with M. Tiger comes after M alphabetically. So you immediately know everything before M can be ignored. You open the middle of the remaining pages. Maybe now you are around S. Now tiger comes after S. Again eliminate half. You keep doing this until you reach tiger. That's binary search because the dictionary is sorted. And the sorted order allows us to throw away half the search space at every step. Now that we understand the idea, let's translate it into code. Binary search usually keeps track of 3 important positions. The first is called left. It represents the beginning of the search range. The second is right. It represents the end of the search range. And the third is mid. It represents the middle position. Initially, left points to the first element and right points to the last element. Then we calculate the middle. After comparing the middle value with the target, we move either left or right. This is how we keep reducing our search space. Now let's understand the implementation line by line. First, left is assigned with value 0. We start from index 0. Then right is assigned with array length -1. This gives us the last valid index of the array. Together left and right define the portion of the array we are currently searching. So right now we have to search the complete array. Next we have while left is less than or equal to right. This means continue searching as long as there is still a valid range to search. Inside the loop, we calculate the middle. Mid equal to left plus right minus left divided by 2. This is a safe and commonly used way of calculating middle index. Now comes the most important part. If array of middle equal to target, if the middle element is equal to our target, we have found it. So we simply return the index. Next, if array of mid is less than target, suppose the middle value is smaller than our target. Because the array is sorted, the target must be somewhere to the right. So we make the left as mid plus 1. We are saying ignore everything up to and including the middle. Otherwise, the middle value is greater than our target. So the target must be on the left. So we move right equal to mid minus 1. Again, we are throwing away half of the remaining search space. Finally, if the loop finishes without finding the target, return -1. This tells us that the target doesn't exist in the array. Let's perform a complete dry run using our logic. Our array is 10, 20, 30, 40, 50, 60, 70, 80 and 90. And our target is 70. Initially, left is equal to 0, right is equal to 8. So, mid is 4. The value at index 4 is 50. Is 50 equal to 70? No. Is 50 smaller than 70? Yes. Therefore, the target must be on the right side. So, we update left equal to mid plus 1. That means left is now 5. Right remains 8. Now we calculate the middle again. The middle index is 6 and array of 6 is 70. That's our target. So we return index 6. Done. Only two comparisons were required. Now let's look at the other possibility. What if our target doesn't exist? Suppose we are looking for 65. Our array contains 10, 20, 30, 40, 50, 60, 70. First we check the middle. That's 40 or 50 depending on how the midpoint is selected. Since 65 is larger, we move right. Then we continue narrowing the range. Eventually, we reach a point where there are no elements left to search. At that point, left becomes greater than right. The while loop stops and we return -1. So the result tells us 65 was not found. Now let's analyze the time complexity. The best case occurs when the target is exactly the middle element during the first comparison. We only need one comparison. So the best case is O of 1. But what about the worst case? Every time we perform a comparison, we eliminate approximately half of the remaining elements. That's why the number of comparisons grow logarithmically. So the worst case time complexity is O of log n. The average case is also generally O of log n. This is dramatically better than linear search where it's O of n, worst case complexity. Now, let's look at space complexity. Our implementation uses only a few variables, left, right, and mid. We don't create another array. We don't create a list containing the elements. We don't use recursion, so the extra memory remains constant regardless of how large the input array becomes. Therefore, the space complexity of this iterative binary search is O of 1. This is another reason this implementation is efficient. Let's discuss some common mistakes. The first mistake is trying to use binary search on unsorted data. For example, 40, 10, 70, 20, 90, 30. That is our array. We cannot simply look at the middle and eliminate half. Why? Because the elements are not ordered. We don't know where the target could be. So before using binary search, always ask, is my data sorted? If not, either sort it first if that's appropriate or use another searching strategy. Another common mistake happens when updating right and left. If the middle value is smaller than the target, we need to search the right side. So we use left equal to mid plus 1. Why plus 1? Because we already checked the middle. We know it is not the answer. There is no reason to check it again. Similarly, if middle value is larger than the target, right equal to middle minus 1. Again, we remove the middle because we have already checked it. These small details are important because incorrect boundary updates can cause wrong answers or even infinite loops. Let's compare the two algorithms. Linear search is extremely simple. It works on both sorted and unsorted data, but it may need to check every element. Binary search is more efficient. It repeatedly eliminates half of the search space. But there is one condition: the data must be sorted. So, which one should we choose? If the dataset is small or unsorted and we only need to search once, linear search may be perfectly fine. If the data is sorted and we are performing searches on a larger dataset, binary search is usually a much better choice. If you remember only one thing from this video, remember this. Linear search says I'll check the elements one by one. Binary search says I will make one smart comparison and eliminate half the possibilities. That's the fundamental difference. Binary search is not faster because the computer is doing some magical operation. It's faster because the algorithm is reducing unnecessary work. This is exactly what algorithmic thinking is about. Let's summarize everything. First, binary search requires sorted data. Second, we check the middle element. Third, we compare the middle with the target. If the target is greater, we search the right half. If the target is smaller, we search the left half. Then we repeat the same process. The worst case time complexity is O of log n, and our iterative implementation uses O of 1 extra space. Once you understand these 6 points, you understand the core idea of binary search. So far, we have learned that binary search requires sorted data. But that raises an interesting question. How do we actually sort data? What algorithms can arrange numbers from smallest to largest? And why are some sorting algorithms much faster than others? That's where we will go next. In next part of the series, we will start learning sorting algorithms. We will begin with a very simple sorting algorithm called bubble sort. We will understand it visually, implement it, perform a complete dry run, and analyze its time and space complexity. If this explanation helped you understand why binary search is so much faster than linear search, please like the video and subscribe. If you are following the series from the beginning, don't skip the next episode because we will now move into sorting algorithms. And remember, don't just memorize O of log n. Understand why binary search is O of log n. It repeatedly cuts the search space in half. Thanks for watching, and I'll see you in next episode of Mastering Algorithms.